Hello everyone. I want to welcome you to another section where we would continue on how to read an IR spectrum. In the previous lesson, I was able to share with us how to determine saturation or unsaturation within the IR spectrum that is given unto us. So in this lesson, I'll be moving further to give us what we still need in order to read the IR spectrum correctly. But in this lesson, I'll be focusing on carbonyl compounds. So how do I identify a spectrum that that has carbonyl functional group? That's what we want to look at in this case. Now there are many compounds that have carbonyl functional group. For example, we have ketone. Ketone has carbonyl functional group. We have aldehyde. We have carboxylic acid. We have ester. We have amide. Amide also have carbonyl functional group. So, and at the same time, we also have acid anhydride. So, this set of compounds I mentioned, all of them have carbonyl functional group. It implies that the spectrum can represent any of the aforementioned compound. That is, it can be aldehyde, it can be ketone, it can be anhydride, um, it can be amide, and it can also be either your carboxylic acid or even your ester. So we are going to be looking at how to differentiate between this set of compounds when you can see a signal for carbonyl, and that's to be the focus of this particular lesson in this video. Generally, the the signal for carbonyl is usually found within 1700 to 1800. So if you see a signal between 17 to 18, if you see a signal between 17 to 18, it's usually for what? For C double bond in stretching vibration. So the vibration frequency for C double bond O is usually found between 1007 to 1008. So anytime you see a signal within this range, it represents your carbonyl compound. Another way of identifying carbonyl signal is by checking for what we call an overtone. So most times the signal for carbonyl usually have an overtone, and overtone is twice the fundamental frequency of particular signal. So for example now, if I have a signal at, let's say, 1007, which probably represents the carbonyl stretching vibrational frequency, the overtone for that particular signal will be at what? At 3400. So, but one thing that is particular about overtone signal for carbonyl group is that it always have low intensity. But you can always look for that overtone signal to confirm that the signal you have between 17 to 18 is certainly for what? For C double bond O. Another thing I also want to note for this signal between 17 to 18 is that in some cases the signal might fall below 1700, and this usually occurs when the carbonyl functional group is conjugated to another double bond. So in a conjugated carbonyl compound, the vibrational frequency for this double bond O might fall below this, because generally conjugation tends to lower vibrational frequency. So it means that anytime your carbonyl signal is conjugated to a double bond, there is tendency that the signal for the carbonyl will fall below 1700. But if at all if it's going to fall below 1700, it shouldn't be less than 1006. But the major region for carbonyl signal is between 17 to 1008. So it's only probably conjugation effect or probably mesomeric effect that can make the signal for this carbonyl to fall below this region. So if there is no conjugation and if there is no mesomeric effect within the compound, then you can be certain that the signal for carbonyl will be between 1007 and 1800. And I've said you can always check for overtone, which is two times the fundamental frequency of your carbonyl, to confirm that you are having certainly a carbonyl signal within this particular region. Now, if you have an IR spectrum and you see a carbonyl, a signal within this region, how do you now know which class of compound the spectrum is having? That's the next thing to discuss. So I have said that carbonyl functional group is present in different class of compounds. So first one is the ketone. So ketone has carbonyl functional group, and it is usually RCO, that is ketone. For another one is we can also have aldehyde. Aldehyde aldehyde is RCHO. That's C double bond OH. So another class of compound that also contains carbonyl is the carboxylic acid. Carboxylic acid, which is RCOOH. Another one that we have is esters, your alkaloids esters, which is RCOOR. Now, I also mentioned earlier that you can also have amide, which is you can have amide, which is RCO. We have NH2. So this is amide. This is ester, carboxylic acid, and aldehyde ketone. At the same time, we can also have acid and anhydride, which is RCOO, and we have OCR. So in acid anhydride, we are having two carbonyl functional group in this acid anhydride, but all other ones that we mentioned there, we are having just one carbonyl functional group. So a signal within this region represents any of these can represent any of these class of compound. So it is now our responsibility to find out which one of these compound is represented within the spectrum. So there are specific signals to always look out for to confirm whether you are having any of these signals, and I'll be giving us information about these signals for each of these class of compound. First, let me start with this acid anhydride because it's like the only class of compound that is different from these other five that I've mentioned here. Now, from acid anhydride, if your IR spectrum represents acid anhydride which contains two carbonyl signals, one of the things you are going to see is that within this 1007 and 1008 region, you are going to see two signals. You are going to see two signals that represent the two carbonyl functional group within this compound. So instead of having a single sharp signal within this region, you are going to see two sharp signals within this region which represent the two carbonyl functional group in the what? In the acid anhydride. So if I could see two sharp signals within this region, that implies I'm having an acid anhydride. But for every of these other compound that you have here, you will only have a single sharp signal within this region because they only contain one carbonyl functional group. So that makes this a bit different from others. Now, to talk about other ones now that we have, let's also talk about aldehyde. For aldehyde, if an IR spectrum represents aldehyde, one particular signal that is only seen in IR spectrum of an aldehyde is a signal at 27, at around 27 what 28. Now, when you see a signal around 2728, this signal is always for the terminal CH of what? Of aldehyde. It's only aldehyde out of all of these compounds I mentioned here that has a terminal CH bond within it. So that the signal for that terminal CH bond at the head of aldehyde compound is usually found between 27 to 2008 per centimeter, and this is only specific for what? For aldehyde. you don't see a signal within this region, that means the compound is not anhydride, and no other carbonyl compound can have this particular signal. So this is only specific for aldehyde. So if you see a carbonyl signal within 17 to 18, and you are seeing a signal at 27, between 127 to 8, then you can say it is what? It is an aldehyde. Now another one that I also want to talk about is these two. Now, for these two compounds, one way of identifying them is by checking for C single bond O stretching fibration, because they are the only they are the two compounds that contains C single bond O. So C single bond signal actually find between 1002 to 1000. So you can find a signal for C single bond O stretching vibration, stretching vibration, which is between 12 to 1000. Then that confirms that you are having carboxylic acid or you are having an ester. So this single bond O stretching vibration is established that the carbonyl compound that you have is either a carboxylic acid or an ester. So that's how to identify these two. But the question now is, how do I differentiate them? So the difference between these two is usually identified by checking for OH stretching vibration, which is usually a broad signal around 3000. So I'm saying that for carboxylic acid as it were, we are going to have a broad broad OH signal around around 3000. Let me give the range. Let's say between 31 to 28. So the signal will look like this. The signal will be very broad like this. You can see a very broad signal like this. So that's what I mean by broad. So if I'm saying sharp, I mean something like this. So you can see this one is sharp, this one is broad. So for the OH functional group in carboxylic acid, the signal is usually what? It's usually broad, and it's usually between what? Between 3000 to 2008. So this signal that you have here is specific for carboxylic acid and not found in what? In an ester. So that means if I have a signal within this region, and I could also see a signal between 12 to 1000, together with this broad signal around 3000, that means I'm having carboxylic acid. At the same time, I could see a carbonyl functional group with only C single bond O stretching vibration around this region. Without this, that implies I'm having an ester. Now, the next class of compound I want to talk about is the amide. For amide, there is one specific signal you can always look out for in amide, in an IR spectrum that represents what's called an amide. Apart from the first thing is to see a signal between 17 to 18, which represents the carbonyl functional group in amide. Another signal to look out for is a signal, is a broad signal, at, let's say, 3000, around 3003 per centimeter with spikes. So when you see a broad signal at 3003 with spikes, it represents your NH2 stretching vibration. So when we are saying we have a broad signal with spikes, so you can have something like this. So what that implies that I have something like this and this. So these are what? These are spikes. So for NH2, which is only present in this amide compound and is not present in other carbonyl compounds, you always see, apart from this signal for carbonyl, you also see a broad signal at around 3003 with what? With spikes. That is how to identify an amide. And the last one is what is ketone. Now, how do I identify ketone? If I look out for all these kind of signals, if I look out for any of these signals that I have that identify different class of carbonite that we have at this side, and none of them is here. So if none of these aforementioned signals which represent different class of carbonyl compounds are absent, then you can say you have a ketone, and that makes the work more easier. But this, like I said, are different signals you can always look out for to identify what kind of carbonyl compound your IR spectra represents. And with this, I am certain that you can always identify, you can always read your IR spectrum to get the correct class of compound that it does represent. But another thing I also want to say is that while we talk about all of these things, you can have a saturated carbonyl compound, you can also have an unsaturated carbonyl compound. So when you are reading your IR spectrum and you could see a signal for C double bond O, and you could identify what class of carbonyl compound the IR represents. You should also try to look for whether the carbonyl compound is a saturated one or whether it is an unsaturated one. And that still goes back to our previous lesson that you can always check for signals around 3000 to determine whether the carbonyl compound given to you is saturated or whether it is unsaturated. So in summary, to read your higher spectra that represents carbonyl compound, the first thing to look out for is a signal between 17 to 18, which represents C double bond O stretching vibration. And we said if there are two signals within this region, it represents the acid and hydride. If there is only one signal within this region, it represents either your ketone, your aldehyde, carboxylic acid, ester, or amide. Now, how do we differentiate between these ones? If I'm having just a single signal within this region, for amide, you are going to see a broad signal at 3003 per centimeter with spikes, which I said is a signal that looks like this. For a carboxylic acid at the same time for an ester, you are going to see a signal for C single bond O within 12 to 1000. But to differentiate between these two class of compound, you have to look for whether the spectrum is containing a broad signal between 3001 to 2008, which represents your signal that you have only in carboxylic acid. And also I said specifically for aldehyde, the signal that identifies an aldehyde is this signal between 27 to 28, which represents the terminal CH bonds. Yes, the terminal CH bond of aldehyde compound. And I said last week that if any of these is absent, then it means that the spectrum represents a ketone. And that is how to always read an IR spectrum that represents a carbonyl. And to remind us, don't forget that I said that in some cases, the signal for carbonyl can also fall below this region, but that would be in the case whereby the compound has conjugation or probably it can undergo mesomeric effect. But if none of these two effects, which lowers the vibrational frequency of bonds, if they are absent, then you can be certain that the signal for carbonyl will be between 17 to 18. And I also said that signals for carbonyl usually have an overtone, which is always found at 2 times this fundamental frequency for the carbonyl. And don't forget to always check for saturation or unsaturation if present in the carbonyl compound that the IR spectra represents by using some of the things that we have talked about in the previous lesson. Once again, I want to thank you for watching this video. I want to plead with you to continue to watch and to share with people that you know can also be in need of this lesson. And please do well also to subscribe to this channel. And if you have any question on any of these things we are discussing, you can do well to drop your question in the comment section. I will be willing to respond to your question. Thank you for watching. Stay blessed and please subscribe.